Dear students, in this video lecture, we are going to continue the line coding techniques, how the digital data will be converted into the digital signals. For that, we are discussed about, we have three techniques, line coding techniques, block coding techniques, and scrambling. So the previous video, what is line coding techniques? So what are the problems are there that we are discussed. In this video, we are going to discuss about different types of line coding techniques. Okay. So in this video lecture, we are going to discuss about the line coding techniques. Okay, this is continuation of the previous video. So in this video, we are going to discuss about line coding techniques. If we are able to interpret the digital data into digital signals using line coding techniques. We have three techniques, but in this video, we are going to discuss about line coding techniques. So this is the classifications of line coding. Okay. So you just see this diagram. We have 5 types of line coding techniques are there: unipolar, polar, bipolar, multi-level, and multi-transition. So these are the some methods under these techniques we are going to discuss in this lecture. So first we are going to discuss about unipolar. So here line coding techniques. First we are going to discuss about unipolar. Okay. All signal levels are on one side of the time axis, either above or below. Okay, either above or below. NRZ model for unipolar. Okay, non-return to zero model. In this scheme, what they are going to do? The example of this code, the signal level does not return to zero during the symbol transition. Okay, it is not returned to zero. The scheme is prone to baseline monitoring and DC components. It has no synchronization or any error detection. It is simple but costly in power consumption. How it is there? You just see the, if any one of the side only. Okay, so here unipolar non-return to zero scheme. So what it is happened? Here 0 is there, positive voltage is any one of the side, that it will be transmitted. 1 means positive voltage. If 0 means there is no signal. Okay. So here 1 means it's represent 111, that above line, timeline. If there is no below line. If we are represent the below line means there is no above line. So only one side it will be mentioned. Okay. How we can calculate this normalized power equal to, so V square or 0 square. Okay, so total how many is there? Voltage we can consider or 0 we can consider. So half into V square plus half into 0 square. Finally we are getting half V square. We are getting half power only. Polar NRZ method. Okay, so in this method, what we are going to do, the voltage are on both sides of the time axis. Okay. So here, what we are going to do, the NRZ scheme can be implemented with the 2 voltages. Okay, positive voltage for 1 and negative voltage for 0. Okay. So there are 2 versions. NZR level. Sorry, here once again. So NRZ level and NRZ inversion level. Okay. So NRZ level means positive voltage for one symbol, negative for the other symbol. Okay. But NRZ inversion, what will be happen? The change or lack of change in polarity determines the value of the symbol. One symbol inverts the polarity, a 0 is does not. Okay. So this is normal. Okay, non-return to 0 level, positive voltage for one symbol, negative voltage for another symbol. But here the inversion technique will be there. Whenever the symbol 1 is there, the polarity will be there. 0 means there is no polarity. that we will discuss with the diagram. You see here NRZ level. What happened? So NRZ level means it may be in the positive voltage means one is opposite one. Okay, so 0 is positive voltage, 1 is negative voltage. Wherever 0 is there, there is a positive voltage. Okay, so wherever 0 is there, there is a positive voltage. Wherever 1 is there, there is a negative voltage. So like that we can use for NRZ-L model. But here NRZ inversion technique, what will be happen? So it will send the signal as positive voltage. It will read the next data. The data is 1. 1 means inversion should be there. Okay, so 1 means inversion should be happened. Then inversion means it will goes to opposite signal. It will transmit. Okay, so negative voltage. Then it will check the next bit. Next bit is 0. There is no inversion. Again next bit 0. No inversion. Then you will see that next bit is 1. So 1 means what happened? Just it will be inverted to opposite signals. So here negative, here positive. So then it will check next voltage is 1, then opposite value, then negative. Then 1 is there, then again it is positive. So again it is 0, there is polarization is not there. Okay. So when the inversion is happened, next bit is 1. If next bit is 0 means there is no inversion. Okay. This is NRZ model. Okay. So NRZ-L is the level of voltage determine the value of the bit. Okay. But in the inversion, what happened? The lack of inversion determine the value of the bit. So inversion will be determined. So both have an average signal rate of n baud. So NRZ-L and I both have a DC component problem and baseline wandering problem. Okay. It is worse for NRZ-L. Both have no self-simulation, no error detection. Both are relatively simple to implement. So what we have concluded with NRZ-L and NRZ-I, implementation is easy, but there is a problem with DC component and baseline wandering, as well as self-simulation is not there, error detection also not there. Okay, but implementation is very easy. You just remember it. Next technique is polar RZ. Okay, what is polar RZ? Return to 0. Previously we are used is not return to 0. But here the scheme is return to 0 scheme. Uses 3 voltage. What are the 3 voltage? Plus 0 minus. So 0 also one of the voltage we are used. That means there is no signal. Positive voltage, negative voltage, there is no signal. Okay. So each symbol has transition in the middle. Okay. So how it will be happen? Either from high to 0 or from low to 0. So return to 0 means center, if 0 is there, this is the 0 line. Either it is negative to 0 or positive to 0. So either it may be will go to 0 or it positive to 0. So this will be the return to 0 scheme. The scheme has more signal transition, 2 per symbol. Therefore requires a wider bandwidth. No DC components are baseline wandering, but self-simulation it is there. Okay, but while understanding it is more complex because we are using 3 voltage levels. Okay, it has no error detection capacity. So see here, this is the 0 timeline amplitude we are representing. Whenever we are saying that it will be 0, 0 means it will comes to 0 in the middle of the transition. Okay, so this is the line. So this is the total signal line. So middle of the transition, it will transmit, and if it is 0 means it will go negative to 0. If it is positive 1 means positive to 0. Okay, so the middle here also will take this entire signal. So here in the middle the transition will be happened and it will return to the 0. Okay. Here R equal to 1 by 2. Why? Because here one signal, here one signal. So 2 signal for one data rate, then 1 by 2 or equal to 1 by 2. So now we are going to discuss about polar biphase method. So in this method, Manchester and differential Manchester coding. So what is the use of this? The Manchester coding consists of combinations of NRZ-L and RZ scheme, return to zero scheme and non-return to zero level scheme. The every symbol has a level transition. Okay, every symbol has a level transition in the middle from high to low or low to high, but uses only two voltage levels. Okay, it is central level, it will be transmission is there, but it is using only 2 voltage, not 3 voltages. In differential Manchester, what will be happen? Same return to zero concept will be there, but we are using the inversion technique. So in the inversion technique, what we are used, the value is 1 means inversion will be there. The value is 0 means there is no inversion. Okay. So see this diagram they are clearly says that 0 means positive to negative. 1 means negative to positive. For Manchester, what happened? For 0 means positive to negative. Here positive to negative. Here positive to negative. Okay. But 1 means negative to positive. Okay. So here 1 negative to positive. Here 1 negative to positive. Here 1 negative to positive. This is Manchester. It's a simple method. But in differential Manchester, what will be happen? Okay. If 0 means there is no transition. But what they are saying that here, just if here they are mentioned that if next bit is 0, inversion should be there. If next bit is 1, there is no inversion. Okay. So here first 0 is there. 0 is there means then it will go for inversion. Okay. So then it will start from negative to positive. Then it will check the next bit 1. There is no inversion. So directly it will start from positive to negative. Okay. So while checking the next bit is 0, the inversion should be there. Inversion should happen in the same line. Okay. So then positive to negative. Then again next bit is 0, inversion should be there. It will goes to opposite direction. Then it will start from the signal transmission. Here 1 is there, no transmission. So signal transmission started from here itself. Negative to positive. Then here there is no 0, so there is no inversion. Then again it will start from positive to negative. This is differential Manchester method. Here also what happened? For single data element, 2 signals we are used, positive voltage, negative voltage. So 1 by 2, R value is 1 by 2. Okay. In Manchester and differential Manchester encoding, the transition at the middle of the bit is used for synchronization. The minimum bandwidth of the Manchester and differential Manchester is 2 times that of NRZ. Okay. There is no DC component for no baseline monitoring. None of these codes has error detection. Now we are going to discuss about bipolar method, AMI and pseudoternary. What will be happen there? The two methods are there. This code uses 3 voltage levels, plus, 0, minus. That means positive, 0, negative to represent the symbols. Note, not transition to 0 as in return to 0. Okay. Voltage level for one symbol is 0 and the alternative is plus or minus. Okay. So while we are discussing about the diagram, you can easily understand. So then bipolar alternate mark conversion means AMI model. That 0 symbol is represented by 0 voltage and one symbol alternates between positive and negative. Okay, alternate model mark inversion, AMI model. That means just wherever the signal 0 is there, that is 0 voltage. If it is not 0, it is 1 means opposite. If positive means previously positive is there means next negative. If negative is there means next positive. Like that it will alternately it will be mentioned. Pseudoternary is the reverse of the AMI. You see the diagram. First, whenever 0 is there, that 0 will be there. 0 is 0 only. Okay. So, but if 1 is there means previously positive, means the next one for negative. Okay. The next one is negative voltage. If in case 1 is there means here positive will come. Okay. So that is alternate marking machine. Pseudoternary is just opposite. So whenever 1 is there, that is mentioning the 0 line. But whenever 0 is there, the positive voltage may be represented to here, then opposite is here. Wherever 0 is there, the alternate will be there. Okay, here minus this plus voltage to plus voltage. Here already plus voltage is there, here minus voltage is there. So these are the techniques used in the line coding techniques. And now just it is a better alternative to NRZ model, as no DC component and baseline monitoring, as no self synchronization because long run sum zeros result in no signal transition, and there is no error detection also. So now we are going to discuss about multi-level schemes. What is multi-level schemes? In these schemes, we increase the number of data bits per symbol, thereby increasing the bit rate. Okay, what is our goal? We have to increase the bit rate with less signals. Since we are dealing with binary data, we only have two types of data elements, ones or zeros. Okay. We can combine the two data elements into a pattern of m elements and to create 2 power m symbols. Okay, we have L signal levels. We can use n signal elements to create L power n signal elements. So now we have 2 power m symbols and L power n signals. We just understand this multi-level transition. 2 power m, that is symbols, is greater than levels. Okay, L power n, then we cannot represent the data elements. We don't have enough signals. But in case 2 power m equal to level of signals, we have an exact mapping of one symbol on one signal. Okay, if it is both equal means we can have same signals. If in case less than that level, we have more signals than symbols. Okay, so we have more signal levels is there compared with the data. So there is better noise immunity and error detection of some signals are not valid. So what band they are using? M, B, N, L schemes. That pattern M data elements is encoded as the pattern of N signal elements. Okay, so this is signal element. This is the levels we are representing. In which less than or equal to 2 power m less than or equal to L power n. How to represent it here? So in this method, D represent the binary data and L represent the number of levels and N represent the length of the signal and M represent the length of the binary pattern. Okay. So L equal to B binary, L equal to T for 3 ternary. We can represent B means binary, T means ternary. Okay. Then Q means 4 quaternary. Okay. That we have to remember it. Binary, ternary, and quaternary. So in these examples, we just use that 2B 1Q. Okay. So that means 2 bits, 1 signals. Here, how to represent it? So here plus 3. In this diagram you see plus 3 plus 1 minus 3. So 4 different levels we are used, but the signal is single signal represent the 2 bits. What is the R value? 2. R value is the data element is 2, the signal element is 1. Okay, so the R equal to 2. Then that is how it is represent. Single data element represent the single data bits, sorry, 2 bits. So the R value is 2. How it will be happen? You just see. So the values first 0 0 is there. 0 0 means previous it is positive. So initially it is starting from positive. So the next level is plus 1. If the bit is 0 0 means next level is plus 1. So plus 1 it is there. Okay. Then it will check 1 1. The next data is 1 1. What is the 1 1? So 1 1 previous level is positive. It is previous is positive. Then what it will go? 1 1 means minus 3. It will go for minus 3 for next level because previous level is positive. So minus 3 it will go. The next value is 0 1. So 0 1 is there here. So 0 1. What is the previous value here? It is negative. So then you have to check it here again minus 3. So minus 3 only we are kept. Then next value is 1 0. Okay, 1 0. The previous value is negative. So it will go for plus 1. So it is coming here. Okay. So after reaching the next bit is 0 1. 0 1. The previous symbol also positive. So positive means here plus 3. So the signal will goes to plus 3. Like that, this table they are used for multi-level transmission. So like this, there is redundancy may be happen. So here another technique is 8B6 levels. So there is 6 signal levels are used 1, 2, 3, 4, 5 and 6. 6 signals used for 8 data with 2 levels. Okay. So it is representation is there. So that is how we can represent the data. They are given this table for your reference. Whenever you have time, you just read it. So now multi-transition. Okay, so that means multi-level using multiple channels. So how we can represent it? In that some cases, we split the signal transmission app and distribute it over several links. The separate segments are transmitted simultaneously. This reduces the signaling rate per link, lower bandwidth. This requires all bits for a code to be stored. XD method means that X is the link. Okay. This while we are seeing the diagram, you can get it. Here there is a bit, n number of bits are there. With using different signals are there. So this signal will be transmitted in different channel. This will be transmitted in this channel. This line plus 2 line will be transmitted in this channel. Like that it is transmitting. Okay. So plus 2 will be 250 Mbps speed wire 1. So second, this plus 1 symbols are transmitted through wire 2 with 125 megabaud. Same like that, it is different lines, it is transmitted with the different signals. Okay. So there is synchronization problem and not be there. Multi-transition method. Okay. So there is a typical case and worst case they are given. So first, initial voltage is 0. 0 means 0 voltage they are given. The next bit is 1. So current bit is 0. Okay, what is the next bit? Next bit equal to 1. If next bit 1 means it will going out. So it will check last non-zero level equal to positive. Okay, what it will do? It will go for negative voltage. Last non-zero level is negative, then it will go for positive voltage. Okay, so here you see this method. The first bit is 0, the next bit is 1. It is coming here. The previous bit is, I don't know, the worst case you can take it that it is going for plus voltage. Okay, so if it is in the plus voltage, now it is the plus 2 voltage. What is the next one? 0. The plus voltage, if 0 means, what is that? Next bit is 0 means same value, plus voltage only. Okay, if in case next bit is 1, if next bit is 1 means, what will be happen? Again it will comes to 0. Okay, so this comes to 0. What's the next bit? 1. So 0 came, next bit is 1, then it will check. last non-zero level. What is the last non-zero level? That is positive. So that positive means it will come here. Again, negative voltage. It will come for negative. Then here 0 means same negative only. So same negativity is maintained. The next bit is 1. So next bit is 1 means again it is comes to 0. Okay, so here 0. The next bit is 1. 1 means it will check. Previous bit is negative, then it will go for positive. Okay, so this is the best case. What happen in case worst case? What will be happen? You see here, the starting point is positive voltage. Here they are using 0 voltage. If they are using the positive voltage, 1 means that is, you see here, all the data are 1. What happened? Each time it is the transmission changes are there. Okay. For each time we have to check this alternate mark conversion techniques also. So there is one model is MLT. Three methods. Signal rate is the same as NRZ-L, but because of resulting bit pattern, we have periodic signal for worst case bit pattern for ones. If continuous ones are came means there is a problem. Okay. So finally, we have all categories are there. Unipolar. In unipolar, we are discussed NRZ. In unipolar NRZ level, NRZ inversion technique, 5 phases we are discussed. And bipolar, we are used to alternate mark conversion. And multi-level, we are discussed about 2P1Q, 8P60, and 4D COM5. So finally, in multi-line, we are used to MLT3 techniques. Okay. So now we are discussed about line coding techniques, which is used to convert digital data into digital signals. So now you know how to convert digital data into digital signal using line coding techniques. Okay. Thank you very much for listening this video. The next video we are going to discuss about block coding and scrambling techniques. Thank you very much for listening.